Good day, everyone. Welcome to CST 351 Lesson 2 Intelligent Agents. In this lesson, we'll cover Introduction to Intelligent Agents, their performance, examples, their environment, and architectures. So, to kick off our discussion on intelligent agents, let's consider a statistic. Industry reports project that the artificial intelligence market will contribute over $15 trillion to the global economy by the end of this decade. Now, this immense economic power is built on a single fundamental concept, that is the intelligent agent, which is the core building block of every smart system we use today. So what exactly is an intelligent agent? So as the slide shows, an intelligent agent, or IA, is defined as an entity which could be a software program or a physical robot that achieves specific goals by perceiving its environment through sensors and acting on that environment through actuators. So the two key words there are sensors and actuators. The agent must operate autonomously without needing constant step-by-step human instructions. It must act rationally to maximize its success. Now, the core to AI is that IAs, that is intelligent agents, are the core concepts for building smart systems. They allow us to automate complex problem solving and create machines that can operate independently and adapt to change and help us in the real world. So let's look at an example to make this concrete. Think of a human being. We are intelligent agents in our own right. Our eyes, ears, skin are our sensors for perceiving the world. Our brain processes the information, and then our hands and voices are our actuators for performing actions. Now apply this model to a virtual assistant like Siri or Google Assistant. Your voice is a sensor input. The virtual assistant listens to your voice. It captures the sound using a microphone and then turns it into data and then uses that data to understand what you want and then respond. Its actuator is the speaker it uses to respond, or the software command is sent to play a song. This simple agent-based model is how every complex AI, from a self-driving car to a movie recommendation system, is fundamentally conceptualized. Now that we know what an intelligent agent is, let's look at how it works. The agent-environment interaction loop. This is a continuous cycle, and everything an agent does fits into these 4 steps. The first step is to sense or observe. The loop starts with perception. The agent uses its sensors like cameras or microphones to observe the current state of its environment and gather data. The second step is to think or action selection. This is the agent's brain. It processes the sensor data, uses its internal knowledge, that is its policy, and decides what to do next to best achieve its goal. It selects an action. Now, the third is act. The agent executes the chosen action using its actuators, maybe moving a wheel, speaking a response, or changing a line of code. And then the fourth is feedback. Crucially, this action changes the environment, which immediately becomes new information for the agent to sense, and the cycle repeats. The agent uses this feedback to adjust its strategy and learn over time. We'll look at an analogy shortly. To be truly intelligent, an agent needs 4 core characteristics. The first is autonomy. This is simple. The agent must work on its own. It doesn't need you to tell it every single step. Now think of a Roomba vacuum. For example, you press start and it makes all the decisions about where to go, when to turn, without constant human instruction. That is autonomy. The second characteristic is reactivity. The agent must be able to respond quickly to what's happening right now in the environment. So if a self-driving car suddenly detects a braking car ahead, that is sensing, it must hit the brakes immediately, that is act. It reacts to current changes. Now, the third characteristic is proactiveness. This is the opposite of reacting. Proactive agents plan ahead to reach a long-term goal. A GPS system isn't just reacting to the next turn, it's constantly calculating the fastest route to your final destination. It takes the initiative to plan. And then lastly, the fourth characteristic is social ability. Not all agents have this, but social agents can communicate and collaborate with other agents or humans. So think of a swarm of delivery drones coordinating their routes to avoid mid-air collisions. They work together to solve a shared problem. So a great agent combines all four. It works autonomously, it reacts to immediate dangers, it plans proactively for the future, and it can work with others. These characteristics dictate how complex and helpful any AI system will be. So let's move on to how we judge an agent's success, which we call performance measures. We judge an agent by how well it achieves its designated goals, and this includes efficiency. Does it use few resources like time, energy, and money? Accuracy. How correct are its decisions and actions? Speed. How fast does it respond to the environment and finish its tasks? So our goal is to build a rational agent. A rational agent is one that makes the best possible decisions at every single step, given what it knows, to maximize its success. It's about being optimal, doing the absolute best it can with the information it has, not necessarily being 100% perfect. This is the distinction between rationality versus omniscience. A rational agent is not omniscient. It is not all-knowing. It can't see the future. Its performance is influenced by what it already knows, such as its perception history, that is its memory, and its knowledge base, that is its built-in rules and fact. When we design an intelligent agent, we first have to understand the world it lives in. We call this world the environment, and we describe it using 5 key properties: fully versus partially observable, deterministic versus stochastic, episodic versus sequential, static versus dynamic, discrete versus continuous. So the first property there is fully versus partially observable. The question is, can the agent see everything important in his world at once, or is some information hidden? So for fully observable example, chess is a perfect example because the agent can see the entire board, every piece, and exactly where they are. Nothing is hidden, so the agent has all the information it needs to make a decision or a move. For partially observable example, we have self-driving cars that can only see part of the road. It cannot see around corners or know what the other drivers are thinking. So the agent must make decisions with incomplete information. Now, the second property we are looking at here is deterministic versus stochastic. And the question is, does the same action always have the same predictable result, or is there an element of randomness? So for deterministic example, we have chess. Moving a rook 2 squares forward always results in the rook landing exactly 2 squares forward. The outcome is fully predictable, so it is deterministic. Whereas the stochastic example could be weather. So for weather, even if all the inputs are the same, a rainstorm might not happen, or it might be stronger or weaker than predicted. So outcomes are probabilistic and not certain. The third property is episodic versus sequential. Now, the question is, are tasks independent one-off decisions? Are the tasks one-off decisions, or does every decision affect future ones? That is in sequence. So a typical example for episodic is image recognition. So for example, if the agent classifies one image as maybe a cat, it does not depend on its previous classification, and that does not affect future images. So each decision is independent. Whereas for sequential example, which is definitely something like chess again, each move affects the next move. So decisions are connected in a sequence. So for static, the fourth property is static versus dynamic. And the question here is, does the environment stay still? Does the environment stay still while the agent decides what to do? For static example, we have chess. The board waits until the agent moves, until the agent makes a move. Nothing changes on its own. While dynamic example is driving. So for the self-driving car, other cars move, traffic lights change, pedestrians walk, the environment changes continuously. So lastly, we have the fifth property, discrete versus continuous. So we want to know, the question here is, are the states and actions countable, or are there infinite many smooth possibilities? For example, for discrete, we have chess. Moves are limited and countable. You can move to square A or square B, but not to position in between. So it's discrete. For continuous example, we have this steering a car. The wheel can turn to any angle. There are infinite many values for the wheel position and the car speed. So it's continuous. Now, these 5 properties help us understand how an AI agent perceives and acts in different environments. Now let's talk about AI agent architectures. The agent architectures defines how AI system thinks and acts, and we can classify them broadly into 3 main types based on how they use memory and planning. We have reactive agents, we have deliberative agents architecture, and hybrid agents architecture. So the reactive agents has no memory, no goals. They only care about what is happening right now. It follows simple rule. If you see this, do that. Very simple rule, and it's very fast because it reacts to the immediate situation. A typical example is the thermostat. If the temperature is low, it immediately turns the heat on. It doesn't plan for tomorrow, it just reacts to the current input. The deliberative agent, on the other hand, has strong memory and creates an internal map or model of the world. So it uses its memory and its goals to reason and plan a complex multi-step sequence of actions. It thinks ahead. And because of this, it's slower as it takes time to plan in terms of speed. A typical example is a self-driving car. It plans the entire route, predicting traffic and calculating exactly when to speed up or slow down to reach the destination efficiently. Now, most modern AI systems use a hybrid agent architecture, which combines the speed of a reactive agent and the planning power of a deliberative agent. So it has two parts. The reactive part handles simple instant actions, and the deliberative part handles the big long-term decisions. So a typical example is a smart video game character, which instantly ducks a punch. That's the reactive part, but at the same time is planning to run behind cover and call for backup. That's the deliberative part. So reactive is fast and simple, deliberative is complex and smart, and hybrid gives us the best of both worlds.